I want to work through a problem using free body diagrams and Newton's second law to analyze a situation involving forces. In this particular story, I've got a rock climber who has climbed up to the top of a cliff, and she is carrying a pack by a rope that's dangling down below her, and she needs to lift that pack up. I think she's going to tie the rope onto the cliff or something so she can pull herself up without the rope behind her. Don't ask me if this is a good way to climb rocks. Probably not, but it's a story. My question is, what is the tension in the climber's upper arm that she's holding onto the top of the cliff with while she lifts up the pack with an acceleration of 5.0 meters per second squared as it's lifted up? That's our scenario. So okay, how do we solve this problem? How do we analyze this problem? In general, what we want to do to solve any force problem is to identify systems that we're going to analyze. So a good place to start is a simple system. Here's the pack down below. It's not attached to very many things. So I'm going to be very explicit about this. I'm going to draw a dotted line around the pack, indicating that is my system. And that's my dotted line. What I'm going to do, I'm going to make a list of all the forces on the pack and put them into a free body diagram. So here's my pack's free body diagram. And what is a free body diagram? Well, I draw a dot to represent the object. It's very simplified in this case. And I'll start by asking, are there any long-range forces on the object? In this case, the pack has a mass of 10 kilograms, so I know gravity is going to be acting on it. We're near the Earth. So there will be a force of gravity acting on the pack. Some people use a W for weight for this. Whatever you use, whatever notation you use, there's a force of gravity on the pack. Also, that's the only long-range force. There's no electrical or magnetic forces acting on this. So then we talk about contact forces. To look at contact forces, I just follow my dotted line. Where does the outside world cross my dotted line? And, well, there's a contact point right here where the pack is touching that massless rope up above. That means the tension in the rope is pulling up on the pack. So I will write down there's the tension acting on the pack that is going to pull upward. That's all the forces. Those are the only two forces in this problem. So, all right. Next up then, as part of my free body diagram, I always include a note on the acceleration. Over to the side, I'll draw the acceleration vector. And I've said it's accelerating upward with this acceleration. So here I'm going to draw acceleration of the pack right next to this diagram. By the way, some people will label that as a force net vector in addition to or instead of labeling it as an acceleration vector. We'll talk about why that is in a minute, but point is that's off to the side. And as part of this whole process too, after I've done that, I like to define a coordinate system. In this case, looking at it, everything's aligned vertically along a single vertical axis, so I'm just going to choose the traditional, I'll say plus y, pointing up, is my coordinate system for that free body diagram. Cool. Now, that's one free body diagram that I'm going to talk about. Another system that I might consider, well, I need to have some system where the climber's arm, the tension of the climber's arm, is one of the forces in the free body diagram. To have that happen, I have to have a system that circles around the climber and where the arm sort of breaks the dotted line. Often I like to combine two systems together, the climber and the pack, but I'm not allowed to combine these systems here because they're not moving together. The pack is accelerating, the climber is just hanging there. I'm assuming that her arm's mass isn't very significant, so that's not an important part of the problem. So we've got the climber just hanging there. I need a separate free body diagram for the climber. So I will draw a dotted line around the climber, and that's my second system. So I'll draw a free body diagram for the climber. And again, there's a long-range force acting on the climber because she has a mass, 60 kilograms. So gravity is clearly acting on her. Let me draw the dot for the climber. I will have the force of gravity acting on the climber as one of my forces. And then I look at contact points again. Where are the places where the environment breaks the dotted line and contacts the climber? Well, one of them is here, the contact point with that rope. And so that rope is pulling downward on the climber clearly. So there's going to be a tension force on the climber going down that way. Tension climber, I guess I'll label down below. And then The other contact point is up here where the climber's arm is reaching up and grabbing. I refer to it as a tension in the arm, so I will call that a tension force pulling up on the climber on the arm. Tension on the arm, maybe we should just call it TA, make it easier, T sub A. Okay, tension on the climber's arm going upward. Again, I like to label the acceleration here. In this case, the climber's not moving at all, she's sitting still, so her acceleration of the climber is 0. So I'll just note that down over to the side. And again, all the forces here seem to be aligned vertically, so the obvious coordinate system to choose is another plus y going this way. All right, I've drawn some free body diagrams, and I always ask at this point, what's the next step that I do after I've finished drawing my free body diagrams for the systems in the problem? And the answer that I have trained my students to always chant out and give is, after I draw a free body diagram, I write down Newton's second law in components, whether that's an x and a y component separate equations, or whether you write I hat and j hat or x hat, y hat component unit vectors in your one equation. I don't care. We're going to write it in components. Obviously, there's nothing x happening here at all. It's just one dimension. So let me write down Newton's second law. Newton's second law says that F net on the, hang on. Let me get my notation straight. I want to be consistent. The y component of the net force on the pack. So this is the notation I've typically used. Different people use different notation. Fy net on the pack is equal to, okay, for this I just need to write down what this is. I guess I can say it equals mass of the pack times Ay of the pack. Why mass of the pack? Because that's what's inside my dotted line. Anything inside the dotted line is the mass that goes in Newton's second law. And Ay of the pack, I've just said these are the y components. This is the y component of Newton's second law for the pack as my system. So what can I do with this? Well, Fy net of the pack is equal to, I can be completely zombie-like brainless here and just say, well, I've got two forces listed. So Ty for the pack plus Fy gravity for the pack. I didn't have to think for that step at all. I just took every force that's drawn here and I just wrote it down. Y components, because that's what the net force is. It's adding up the y components to get the y component of net force. That's what net force means. Then the next step is where I actually use my free body diagram for more than just a list of forces. The next step I say, okay, T pack here is pointing upward. So that is, upward is my plus y direction based on the coordinates I chose. So I say this is plus T pack, or now there's no y subscript. Now this is the magnitude. I was careful to say the magnitude of this is positive. The magnitude is always a positive number, and the direction is positive plus y, because that's how it was drawn in my diagram. I'm using the diagram to figure that out. Similarly here, my magnitude here is going to be the magnitude of Fg on the pack. And looking at the diagram, I've drawn that force in the negative y direction. So I put a minus sign here. I suppose I even know that this is T pack minus M pack times G, because the force of gravity on an object is just its mass times G, little g, 9.8 meters per second squared. So I'm set. I've got that. My right-hand side now, I can do the same kind of thing. This equals M pack times, and Ay, again, A pack is this upward thing. A pack is positive. So since it's up in the upward direction, that's my positive direction that I chose. So I put in plus A pack is the magnitude there instead of just the y. Again, to emphasize, the y components have the plus or minus signs inside of them. You just add up the y components here. There's no plus or minus signs in this step. But inside of FYGP was the minus sign, the negative for the direction. Inside of TYP was the plus sign for its direction. Those are built in when you write y component. You don't want to have minus signs floating around there. All right, so I've got Newton's second law for the pack pretty much set. I can do the same thing down here for the climber. Same story. I say that Fy net for the climber equals mass of the climber times Ay for the climber. I know that's going to be 0, so this whole thing will be 0. That's an easy step to do. And for my net force, again, my first step writing down the components is completely brainless. All I do is I just take the list of set forces and I say y component of the tension in the arm plus the y component of the tension on the climber from below plus the y component of the force of gravity on the climber. No minus signs here because any directional information is inside the components. Now in the next step I do that. I say this is, well, tension to the arm is up, so that's going to be plus the magnitude of the arm tension. Tension on the climber from below is down, so that's going to be minus the magnitude of the arm tension and minus the force of gravity magnitude on the climber, or just to spell that out, tension of the arm minus tension here minus m climber g equals 0. Copying down that equals 0 from above. And at this point, I like to underline unknowns in my equations, just to sort of highlight what those unknowns are. What are my unknowns? Well, up here, tension pulling on the pack is an unknown, but the mass of the pack was given, acceleration of the pack was given, g is known, so that's there. And down here, tension in the arm is my ultimate unknown. That's what I'm really trying to solve for. Tension in the cable, on the climber from below is unknown. These are knowns, though. It looks like I have 2 equations in 3 unknowns. But fortunately, I happen to know a crucial fact about tension, and that is that as long as this is an effectively massless cable between the pack and the climber, or massless cord, or whatever it is, as long as it's massless, and then I can assume the tension on each end is equal. And what that tells me then is that tensions are equal. That tells me that the tension on the pack equals the tension on the climber from the cord below. And that gives me a 3rd equation in my 3 unknowns. 3 equations and 3 unknowns, that's solvable. I can do that. And so let me solve that problem. Let me just come over and figure it out. Well, what will I do? I guess this is my ultimate unknown. I need to find tension on the climber from below, which is this. Okay, my plan then, I'm going to start here with T-pack. I'm going to bring this up. I'll say that T-pack is equal to mass of the pack times g plus mass pack times acceleration. I'm going to combine those. G plus a pack. Cool, I've got that. And this is equal to tension C because of this equation for the tensions. And so now I'll bring this up and I'll say tension in the arm is equal to tension on the climber from below plus mass of the climber times gravity. But now I'll bring this in and I'll write it down as mass of the pack times g plus AP plus mass of the climber times g. And I have an equation for the tension in the climber's arm in terms of things that I know. I guess I can plug in my numbers now. Mass of the pack is 10 kilograms times 9.8 meters per second squared plus 5.0 meters per second squared plus 60 kilograms times 9.8 meters per second squared. And if I put all that together, I can add up those numbers, and I have done this earlier. I get 148 newtons plus 588 newtons, which comes out to be not 600, 736 newtons, I think, is my answer. So there's the story. I worked this out by drawing free body diagrams for each of my 2 systems. I couldn't combine them because they were moving differently. Free body diagrams for each of my 2 systems, and each one led to Newton's second law. I was careful with the plus and minus signs for direction. I imposed the constraint that the tension was the same on both ends of a massless cable, and then just solved some algebra to get a final result. It seems plausible to me. 600 newtons is about right for a 60 kilogram person. This is more than that, but not a huge amount more. Seems in the right neighborhood. There are probably other double checks I could do, but really I don't care about them right now. I guess I could say, hey, if the pack was massless, would this come out to be the right answer? And sure it does, because it wouldn't be there at all. If the pack were falling, what if the pack were falling? What if the person dropped the pack, so its acceleration was minus 9.8 meters per second squared down? Well, a pack would be minus g in that case, because it's opposite the direction I drew it here. If she dropped the pack, and minus g plus g would cancel out, and I would just have mass of the climber times gravity. That seems reasonable. The formula seems to be sensible to me, so I have a fair bit of confidence that I came up with the right answer here. That's the idea of how you can solve a problem using free body diagrams to figure out unknown forces and relate them to accelerations and things in a scenario like this.